So we're going to be talking about polarity. And we sort of introduced it before, but we didn't really talk all the way about it. Polarity is basically an unequal sharing of electrons. And what we see when we have polarity is a positive and a negative end. There's two key words here that we want to pay attention to. They are sharing and molecule. So if you think about those two words, the only type of bond that we've talked about that shares electrons is going to be a covalent bond, which are also known as true molecules. So when we're talking about polarity, we will be talking about our covalent bonded substance. It's also important here to remember what we talked about electronegativity. So if you remember, electronegativity is a trend on the periodic table, and basically it increases up and to the right. Our noble gases are not included in electronegativity because they're not really going to go out there and bond. And then we have fluorine, which will have an electronegativity value of around 4. And then francium is the least electronegative element down here. So they go anywhere from a little bit close to 0 to 4 as far as values go. So that's something that we already talked about. So when we're talking about our bonds, a nonpolar covalent bond is going to be a bond that shares electrons equally, something like Cl2. So I like to think of like twins with the same attractiveness, they have the same personalities, and so they have equal attractiveness towards electrons. So if you imagine that those two little dots are my atoms, remember when we're sharing electrons, the electrons are moving back and forth in the electron cloud. So they're moving back and forth between these two atoms. And so what's going to happen is we're going to see an equal movement where the electrons spend their time equally with each atom. They're not spending more time on one side than the other. And so that's going to be a nonpolar covalent bond. When we see a polar covalent bond, what we're going to see is an unequal sharing of electrons. So if you look at hydrogen and chlorine on the periodic table, they're in very different spots. Hydrogen's on the left, chlorine's on the right. It's right there next to fluorine. So chlorine is very electronegative. Hydrogen, not so much. So chlorine is going to attract a lot more electrons. Electrons are going to want to hang out near chlorine more than they're going to want to hang out near hydrogen. So if I have my two atoms, basically what's happening is they're traveling back and forth at a mix and mingle type scenario. But every time they see chlorine over here, they just want to hang out here a little bit more. And so since my electrons are hanging out here a little bit more and hanging out with my hydrogen less, we start to see a shape like this. And what that causes is what's called a dipole movement, where one side of the atom will become more negative and the other side will become more positive. So that is a polar covalent bond. Just to tell you the difference between that and an ionic bond and make sure you understand, an ionic bond is stealing electrons. So instead of my two atoms sharing, one of my atoms, in this case chlorine, is going to come up and say, hey, sodium, give me your electron. Sodium's going to say, okay. So chlorine becomes negative, sodium becomes more positive. There is no movement back and forth of that electron. It's now with chlorine. But what attracts those two atoms to each other is the attraction of the positive and the negative. So it's not a sharing and movement back and forth like we see with polar covalent. It's a little bit different when we're talking about ion. In order to determine if something is polar or not, we are going to calculate what is called the difference in electronegativity. So the difference in electronegativity is just a calculation that helps us determine which atom is more electronegative in an individual bond. Before I keep going, I want to explain what I mean when I say individual bond. So this is a Lewis dot diagram we did a little while ago. And if you look at this, this is a true molecule shape. So this is a covalent bond, and it's a covalent bond that is going to be a molecule. So this is the molecule. Each one of these lines represents an individual bond. So when I'm calculating difference in electronegativity, I'm going to be calculating the difference between these two atoms. these two atoms and these two atoms. I don't have to calculate it 3 times because they're all the same, but that's basically what I'm going to be doing. So if your atoms were different, you're not going to add the numbers together or anything weird like that. You're just going to do each individual connection. Formula is really simple. It's probably the easiest formula we learn all year. You take the big number, you subtract the small number. That's it. So you should always end up with a positive electronegativity value, and that's going to tell you where you fall. So if the value that you get falls somewhere on this chart, it's going to tell you what that difference is. So if it's between 0 and 0.3, it's a nonpolar bond. If it's between 0.3 and 1.7, that's polar, and then 1.7 to 4 is ionic. We will see some covalent bonds that are so different that they register as ionic. That just means that the electrons are staying over there for a really long time. Same thing for ionic bonds. If they're really close together, we might see them register as polar. That's just telling us about the electron. We will determine if it's ionic or covalent from the periodic table, seeing where they're at. Okay, so electronegativity values, where do we get those? One of two things will happen. I will either give you a chart that gives you all of the electronegativity values for all of the elements on the periodic table, or I will give you the electronegativity values themselves, one or the other. You're never going to be expected to know these numbers, and I will also give you this chart if you need it. So for the purpose of these next few problems, here are the electronegativity values for 3 elements, and we are going to calculate the electronegativity values like we did or for the examples that we did earlier. So first one is Cl2, so we're kind of going to prove that it is what we said it is. Cl2 is just 2 chlorines. Since they are equal, it doesn't matter which one you put first. So 3.16 minus 3.16 gives you 0. And if we look on here, a polarity of 0 is going to be a nonpolar covalent bond. The next example, and if you want to race me, feel free. Next example, I have chlorine and hydrogen. I'm always going to use the biggest number first. So 3.16 minus hydrogen, 2.20. That gives me an electronegativity value of 0.96. And if I look on my chart, 0.96 falls in here. So that is going to be a polar covalent bond. And then the last one, sodium and chlorine. Chlorine's the bigger number. So 3.16 minus 0.93. You do that math, you should get 2.23. And 2.23 registers somewhere in there, which is an ionic bond. So that's one of the ways that we can figure out difference in electronegativity. We use that difference in electronegativity to help us draw the dipole movement. So dipole movement is basically going to be a drawing of the movement of those electrons. So it might involve Lewis dot diagrams or what we talk about later, Vesper diagrams. There's 2 ways to do it. The first way is an electronegativity symbol. And electronegativity symbols are going to show us the movement of electrons in an individual bond. So when I say individual bond, remember I mean one little piece of that Lewis dot diagram. And an electronegativity symbol kind of looks like a figure 8, except it's not connected all the way through. So that was not a mistake on my part. It's just not connected all the way through. So I'm going to draw that. We will see electronegative symbols, and we will also see symbols that have a positive sign next to them, which means that they're more positive. So this one is going to be more positive. If it is more positive, that means we have lost electrons, or electrons aren't hanging out on that side. If it's more negative, that means that this is where our electrons want to hang out. Electrons found here. So that means that's where most of our electrons are going to try and stay, and that will be the more negative side of our polar bond. The other type of symbol that you'll see is called a dipole arrow. And a dipole arrow is going to show us the movement of the electrons in the molecule. So this is sort of like overall, as a whole molecule, what's going on. The dipole arrow is an arrow, and then we just add a plus sign. So the plus end is the more positive, where our electrons are not trying to stay, and then the side with the arrow is the more negative, where our electrons are trying to kind of stay away from there. So we're going to do two examples. You may want to try these Lewis dot diagrams first as good practice on your own, but I'm going to go ahead and get us started. And the first example that we're going to do is for CO2. So if you draw out the Lewis dot diagram for CO2, you will come up with a diagram that looks like this one, or you should, because carbon wasn't happy and we had to form some double bonds. I would also give you these electronegativity values if you needed them. And so we're going to draw these dipole arrows and figure out all the rest. So first thing I'm going to do is I am going to do my electronegativity difference calculation. Remember, it's always the big number minus the little number. So 3.44 minus 2.55. And that gives me a difference of 0.89. If I go back and I look on that chart, that tells me that that individual bond is polar. And since it's polar, that means my molecule is going to get some electronegativity symbols. So the calculation was for the individual bond. So I'm going to cover up the bonds. This is one individual bond. This would be another. So for this individual bond, we know it's polar. And I know that my electrons are going to move towards the more electronegative atom. In this case, it's the biggest number. We could also look at the periodic table and figure it out by looking at fluorine. So oxygen's more negative, and carbon is more positive in that individual bond. If I do the opposite bond, it's the same thing. So oxygen's going to be more negative, carbon is more positive. So that is my electronegativity values. Now we're going to figure out the dipole movement. So overall, as a whole molecule, what's happening? If you think about a gigantic game of tug of war, where the negative side always wins. In this case, we have negative oxygen on one side. We have negative oxygen on the other. And then we have carbon somewhere in between. And there's our rope. So if you're thinking about that game of tug of war and who's going to win, they're sort of equal. They're oxygens on both sides. They're the same electronegativity value. And it's going to be a very long game of tug of war because nobody's going to win. They're equal strength. And because they are equal strength, this molecule will be nonpolar, which means we're not going to have one of those dipole arrows because there is no overall movement for this molecule. Okay, next example is water. So for water, we have H2O, that's its Lewis dot diagram. We actually need to know something else, and we haven't talked about this yet, but we're getting ready to, and that is Vesper shapes. So we're going to talk about the different shapes that different molecules have, but water actually has what's called a bent shape. So the water, or the oxygen molecules in the atom is in the middle, and then we have our two hydrogens that bend down. And the reason that they do that is because of the lone pairs that that oxygen molecule has, or oxygen atom has, excuse me. So this is a bent shape, and this is really important because it's going to play into our polarity, and it's also one of the reasons that we have life on Earth, because of the way that the water molecule bonds itself. So super important, but if we do our math over here, so large number minus small number, we get a difference of 1.24. So they're real different, which tells us that they are definitely a polar bond. So when I draw my electronegativity symbols for this individual bond, oxygen is more negative and hydrogen is more positive. That's because oxygen's closer to fluorine. It's also because hydrogen will never be the more electronegative one. It's too small. And then I'll do the other one. So oxygen is more negative, hydrogen is more positive. Now if I think about my game of tug of war, I have my little oxygen guy, and he is pulling 2 hydrogens along with him, essentially. There's nothing on the other side to really pull him back. And so in my game of tug of war, there will be a dipole movement, and it's going to point towards the oxygen. So I'm going to draw my arrow pointing up towards the oxygen with a plus sign on the side that is more positive. And that is electronegativity. Last little thing for today that I want you to know is like dissolves like. Like dissolves like. Basically what that means is a polar molecule will dissolve another polar molecule, and a nonpolar molecule will dissolve another nonpolar molecule. So we're going to see our polarity play a big role into solubility a little bit later on.